The next application of the magnetic force is the mass spectrometer, sometimes called the mass spec. And the mass spectrometer was invented by physicists, and at one time the only place you ever saw a mass spectrometer was in a experimental physics research lab. But nowadays they're in mass production in various sizes, and uh, uh, virtually every chemist gets trained on a mass spectrometer. They're very useful devices. Forensic scientists, lots of labs have these mass spectrometers. The device is fairly simple, and it plays on the magnetic force. Uh, what I've got is generally you have a metal plate here, and on one side you've got a nice uniform magnetic field, so that's the B naught coming out of the page at me. And then you've got an acceleration unit over here, which is really just another metal plate, and you put a substance here. Think of it as a pure substance, elemental, and you heat it up, vaporize it, and in fact ionize it, and heat it up enough so that all you do is ionize one time, remove one electron from it, and so these will pick up a charge of plus Q in general. Okay? Usually it is the positive Q. It's missing an electron, and so there's one more proton in the nucleus of the atoms than there are electrons going around it, and so we have this Q is the plus Q is plus E. And it's originally just sitting here essentially. I call this point 1 and this one point 2, but I apply a potential difference between this bottom plate and this metal plate up here, the big thicker one. And I do it with an adjustable voltage, which I'm just going to call delta V here, with the high potential side on this side and the low potential on this side. So that means that this plate becomes high potential. That's at V1. And the other side is the low potential, so it's a metal plate, and so this metal plate up here becomes the low potential side. Or this is the positive plate, and this is the negative. Now I've got positive charges here, and so they're immediately accelerated across. They're repelled by the positive plate at the bottom and attracted by the positive plate at the top. Now, some of them may deviate over to one side or the other, but some of them will go straight through. Okay? What the first thing I want to do is I'd like to get a relationship for the velocity with which these particles enter the magnetic field region. So I call that little v. And to get that, I know that in this process from 1 to 2, from the time it leaves here to where it enters the field region, call those point 1 and point 2, that energy is conserved. It's a conservative field, a conservative force, and so I know that the total energy is conserved, so the kinetic energy at 1 plus the potential energy at 1 has got to equal the kinetic energy at 2 as it just enters the field, plus the potential energy at 2. And if we assume it starts off at 0 here, then its initial velocity at 1 is 0. It's Q times it's starting whatever the potential is at this plate. That's the high potential side, right? And by the time it gets to 2, it's now moving with the velocity that it has been accelerated to. I call that V. And the potential energy when it arrives at this point is the potential at this point, which is Q times the potential at this upper plate, which I call V2. And one can then solve that for the kinetic energy, or in fact you could solve it for the velocity. But that gives me one relationship. If you look at this, if I take the 2 over to this side, I'll get 1 half mv squared is equal to Q, V1 minus V2. But V2 is larger I'm sorry, V2 is smaller than V1. I start off at high potential on this side and get up to lower, so this is a positive quantity. And if you like, you could solve this for the velocity in terms of the potential difference that's applied across there, the charge and the mass of the particle that was accelerated. So this particle now has a mass m, and a charge plus q. Well, once it enters the field, a region up here, I know what it does. It undergoes um, a magnetic force, and I know it follows a circular, really semicircular in this case, motion. And so mass times acceleration, it's centripetal acceleration, so it's v squared over r. And the force up in this region is just q v b naught. You can look at it, but again, the magnetic field is always perpendicular to the velocity, and so the angle between v and b naught is always 90 degrees, and so the sine of 90 is 1. And so the magnetic force is the q v b naught, and set that equal to mass times the centripetal acceleration. And I can solve that, well, depending on what you want. You can solve it for v to get the speed, q r b naught. R is the radius that this goes through. So the total distance over here is 2r, but the radius of the circle or semicircle that it goes through is just r. Or it may be that, and probably is the case, that, well, I could, in principle, solve this one for little v, the velocity, and solve it for r. So depending on which one you have, what parameters you have knowledge of, and what you want, you can solve this equation here for either v or r. I call those equation 2 and 3. And first thing, if I substitute 2 for v into 1 up here for v, so I substitute into this equation, I substitute v, which is q r b naught over m, from equation 2. I get this. I square things out, and I get a fair amount of cancellation. And ultimately, I have an m here, and I can solve that for the mass of this particle. And you get this relationship. I know the charge. It was singly ionized, so that's E, usually. R, B naught, I've applied a known magnetic field strength. Usually that's a held fix. You just use one magnet. And the delta V, well, I can adjust that. That's over here. I have adjustable voltage. So in principle, the things that I know in this are Q, B naught, and delta V. I actually have control over the delta V usually. B naught is usually a magnet, and it's going to have whatever the magnet strength is. So if I can measure R up here, so it comes over here, hits at this point. If I can measure the total distance from the entry point to the exit point, that's 2R. So I can measure that distance and get the radius of this circle, semicircle. And then once I know the radius here, then I've got everything, and I can determine the mass of the particle. So a very useful way to determine the atomic masses of atoms, or really atomic masses of anything, of molecules as well. What else should I say here? So we've done that. You could alternatively, so once you've done that, you might say, well, how do I know? How do I get this distance? Well, what you usually do in the early days, you'd put a little bit of fluorescent paint along here, and these particles, when they hit it, would make that a fluoresce, and so you get a little bright dot here, and you'd get a pretty continuous brightness, and so you'd be able to see that very easily. This is just a little pinhole, so you can measure that diameter very easy, take half of it. So really a pretty easy measurement, even easier nowadays. We'll talk about that here in a second. Alternatively, you could, if you rearrange things a little bit, you can, from equation 1, you can solve for the velocity and use that in 3. So I'm going to have this equation 1 solve for the velocity and put that in this equation here. So I'm eliminating now the velocity. And if you do that, here, so from 1, I get this. I plug that into 3, and plugging that into equation 3, I get this, and then a little bit of simplification. And you see, once I've got this, once I've got the mass up here, then I can solve in this sense. Probably the most useful thing is just to know that the radius goes like the square root of the mass. So the larger the mass is, the larger the radius that it goes through. And that is useful in separating different isotopes of the same material. In fact, historically, this was invented. They created one of these beams using uranium ore. And uranium ore is typically naturally occurring on the Earth, is 99% uranium-238 and 0.72% uranium-235. So this one is slightly more massive. It's got 3 more neutrons than this one. You ionize them, accelerate them across. This one is slightly more massive, and so it goes through a larger circle, and its radius is over to here. And the uranium-235 it's less mass, and so it goes through a slightly smaller R in its semicircular motion. And then you could just put a collection bucket here, and you just keep firing this stuff across, collecting uranium-235 in the inner bucket and the uranium-238 in this bucket here. And this was one of the early ways of separating uranium-235. It turns out uranium-235 is much more fissionable than 238, and it was actually this particular isotope, 235 of uranium, that was used in the uranium bombs, the first atomic bombs. So early usage, and really what the physicists had invented for was during the Manhattan Project to do isotope separation. But they recognized that you could use it pretty easily as a way to identify materials. If I've got a mixture of stuff that I'm firing in here, well, the less massive ones will hit over here, the more massive ones will hit over here. Mass A is less than mass B is less than mass C. And then you would, in the early days, would put a piece of photographic film here, but now you just put a CCD camera, so just a digital camera. The one that's most abundant, the more particles that are hitting it, the brighter it gets. So you plot the intensity versus radius, effectively, so the radius out. And what you find is that mass A is maybe the least bright, so it's going to be the least intense. I'm plotting intensity upward. The most intense was this B element, and this the next brightest was this one. And I just said hypothetically you had this brightness was 20% of 100%. This is 50% and 30, so they all add up to 100% of the beam that's coming across your intensity. The location of these, one can use those to identify what the mass is, and if you look those up in a periodic table, you know what these elements are. You also know the abundance. The brighter it is, the more of the mass A there is. The brighter this one is, the more of mass B. So in this presumably unknown sample here, you get information about A, the composition of it, and moreover, you get the percentage composition. So you know the kinds of molecules that are in there and the relative abundances of both of them. Well, nowadays engineers have made this into a push-button operation, so the chemists and the forensic scientists use this device to identify unknowns, essentially.